It'd be so that's the max volume.
Okay, so can you see my screen?
Yes, this is not presentation mode.
Oh, I'm also only using a PDF.
Okay, there's a presentation mode in PDF too. It just blows up
Uh,
and show the whole screen.
okay, full screen.
Probably under view would be my
Yeah,
yeah,
yeah.
yeah, that's good.
But yeah, only three slides. So hello everyone. Today I'm going to do a
Yes, yeah.
uh,
I guess the speakers.
fluid workshop in lab.
Sorry, one moment, Yuanhao. We're gonna try to get the volume up a little bit on here. We'll have to basically work out. So select a speaker, same as system, test speaker.
The speakers via USB 2.
Yeah, the speakers via USB. Actually, so
I'll connect my laptop.
you'll connect your laptop. Oh, okay.
Yeah.
So Tarsh, is that okay with you? Sorry, Yuanhao, just one moment. Why don't you go ahead and get on Zoom? And
It's
then,
the M5 laptop.
Yuanhao, which Zoom are we in right now? Now, is this yours?
My personal Zoom. The
Okay.
link is in HD Slack channel.
Sure.
Thank you. This way we will get much better volume out of this. And just for the purpose of estimation, you don't have to feel pressure to say any particular number. Yuanhao, what do you estimate the lecture length will be?
It will be like half an hour.
Okay. All right. Good. Or we could make it. What is it? I don't know. If the mic works separately, sometimes we just put the mic close to the speaker of the laptop.
You could, although now you are subject to all kinds of inadvertent feedback that could happen because you've attempted to create a coupling just through proximity.
Yeah.
That's like,
Sometimes it works. And Sakeshi, what do you anticipate your time will be?
I don't think I'll be able to get through all of it.
So, what number does that correspond to?
I mean, I'll
If
teach
you
as long as you
could answer
guys.
a number, what number would it be?
I'll teach as long as you guys are interested. So.
That is a recipe for disaster because different people have different levels of interest, and you don't want to put people in a position to see. This is why like classes have appointed end times, so that nobody has to. If you don't like it, you're sitting here until 5:30. If you like it, you're sitting here until 5:30. You can go to office hours afterwards if you want, but class ends at X time. So you should say it ahead of time so that you don't make people confess whether they're interested or not.
Well, I have to leave at around 7, so you could.
Okay, that would be quite on the long side.
But this is an hour, right?
You're not saying it's going to be a half hour.
Okay.
Without question. Without a question.
Okay. Let us plan on 45 minutes, and then
Okay.
we will adjust.
I think this is a very helpful topic for both the people in our group.
So let's kill the volume on all the other laptops.
This is the volume open.
Mic check. Yes, excellent. All right, Yuanhao, you want to say something?
Yeah, I will continue to present. Okay, is the volume all right?
The volume is great.
Okay. So in particular, I will talk about the geometry buildings for these three systems. It's going from the simple fluid to water to some more complicated fluid. In that case, it's ionic liquid. I will also talk about the interatomic potential setup in these simulations. You should expect that the force field will become more complicated, going from simple fluid to the ionic liquid. And I will also talk about the usage of VMD to build the geometry. So first, let's look at how to build the geometry just using lamps. So we know that lamps can help us to build some geometry files, but this functionality is very limited. If you just want to use lamps to do it, you can only achieve some very simple geometry files. For example, for Lennard-Jones fluid, which is monatomic fluid system, you should have no problem just building it using lamps. So let's take a look at the script that I wrote. So I guess the front is a little bit small. How to make the front to be larger in a text editor?
So this is a good. I'm holding your mic on. Yuanhao, you able to hear us?
Oh yeah. So that's better, right?
Yeah. So this is better. Of course, if you want to make this a little more sustainable, go to preferences in text edit. This is a good lesson all around. Whenever you plan to present or demo anything, it's on you, the presenter, to make sure that you know how to do stuff like font adjustment on the fly. It's all part of being a good teacher. These are things that are completely on you, even if you didn't anticipate it. So go to preferences under text edit. And you can change the plain text font. So just change that from Menlo 11.
How to change this?
Yeah, that's the one.
Change it to what? Bold?
Well, bold's only a little bigger. You can be a lot more daring than that. 13's not lucky. Let's go at least 18, if not 24.
No, it doesn't change.
Unless if this is a rich text file, then you have to change the other one as well.
Okay, I will figure that out later. I think that's enough for you to see, right? Is this, can you see it?
Yep, this seems to be good all around.
Good. So you will see that how I build the initial geometry file in just using lamps. So for the fluid part, I use a create items command. And this part, I will control the number of fluid because I set the number of fluid to be a variable here. And I will use that create items command to create 230 fluid items in that box. So that's how I achieve this simple fluid geometry building just using lamps itself. And I will continue to run this simulation, which is a very standard process in lamps. First, going through the NVT and then record some data in NVE, because this is a relatively simple system. So if I run it, it will be very fast to run. So just using my computer, this whole simulation will finish within several seconds, 5 seconds. And let's visualize the data file. So this is the final data I got. And you can see that how easy, if you just want to build a simple fluid geometry, just using lamps will be enough to do that process. And you may wonder how to do that, how to add the carbon walls to provide the solid nano confinement to this system. So the current method I use to build these carbon walls, which in that case is a graphene, single layer of graphene. I'm using the VMD to do that. So if you open the VMD software, we are very familiar that it's used to visualize our molecules, but it can also use to build our geometries. If you go to extensions and you go to the modeling session in extension, and there are many options. You can say you can add a solvation box, you can also add ions. And in that particular case, it's called nanotube builder. So so here, let's build a very small graphene layer and generate that sheet. So from here, you can see that the VMD can help you to do that process. So you will get this geometry. And the way to save this geometry is you click File, Save Coordinates, and you can select what type of file you want to save. So I prefer XYZ type of geometry file. And then you go ahead and click Save. So let's just save it in this directory, and I will call it 20.xyz and click Save. So if I go back to, so you see I will get that geometry file in this folder. But this is not ready to do the simulation, because if you just visualize this in Ovato and add to, so there are several problems. First, the atomic types, the atom types are the same for the solid and the fluid. So you have to distinguish that in your simulation. And secondly, that there is only one solid wall. You want to duplicate another one. So there are many options to do that. You can use command in lamps to do that, and you can also build this geometry by copying this wall to the bottom to the top. So I will not do it here, but this is just so to make everyone realize that the VMD is a good option when you want to build some, like when you want to use the extensions to build some initial geometries. VMD is an option here. And there is another video that I previously recorded, which I talk about how to make some good images in VMD. Probably we are all familiar with Ovato usage, but we have not used VMD a lot. So what question do you have? Sorry, I cannot hear you very clearly. I cannot hear you.
That way, sitting in the back of the classroom. Even for our flip type of the chat, it's like a 21st century classroom.
No, I have not tried making this graphing sheets in Ovato. But one thing I can tell you that you can, so now the geometry file is XYZ file, right? So if you load this XYZ file in Ovato, and let's replace this selected. Maybe I need to restart the Ovato. So if you, just one second, it will restart. If you load this XYZ file in Ovato, you can very easily transfer that XYZ file to a LAMMPS data file. So how to do that? Export file. And there's a selection, you can save that as a LAMMPS data file. Save as, for example, 20 carbon.d. Okay, and I will hit save. So hit OK. And you will see that there is a data file that has been saved out. But okay, so now it's getting better. But we mentioned normally we need to add something to that data file, because you may notice there is no mass option, right? So if you are familiar with how LAMP's data file is made up of, you should add this masses onto that, because and better if you put a carbon option here. So that's how you make a LAMP's data file from an XYZ file. It's very convenient to do it in LAMPS. Sorry, in Ovito. And I will show you this video about the usage of the, this is a previously recorded video. And you can learn how to use the VMD to render better images. Usually something end with a line trajectory. And I will get the effect like a line representation for all the molecules, bonds, and angles in the system. Next, let's go ahead and do some processing here. So what we want to do first is go to representations, and coloring method we want to change based on our color ID. And the drawing method, we would like to make the drawing method more like a molecule. And for that case, we can change the color to any color we want. So the material, we can also select it to be any materials we want. So
hey, Yuanhao, would you mind pausing?
Sure.
Okay.
Yeah, okay, go ahead.
Okay, that was unmuted?
Yeah.
Yuanhao, you able to hear me?
Yeah.
This video, why don't you, is this video something that you put in the Slack before?
No, I have not.
But go ahead, put this video in the Slack so that other people can appreciate it. This is a teaching philosophy thing that, different people have different philosophies. So I'll say my philosophy on this, and I want everybody to try to hold to this. Don't use live class time to play videos for other people. Some people are lazy teachers, so they plan whole semesters just making other people watch videos, which I think is a ridiculous use of class time. But class time is really special because it's this chance where you can interactively engage with people. So if you have pre-prepared videos, send them to people ahead of time and encourage them to, on their own time, watch them and learn this stuff. And then use the class time when you're actually teaching to engage with people. And this is, there's nice material in this video. I think people here will benefit from that. So put this in the Slack. And is this video crucial to the next thing that you want to teach about?
Yeah. So I want to eventually show you the effect of our view to the orthogonal view. And now we are ready to. So this is eventually the thing I want to teach you how to use VMD to achieve that. Basically, you can render very beautiful images that using VMD. It's not. I think it's sometimes you can have more flexible options compared to Ovito in terms of making these pictures. Okay, I will post that video into the Slack channel later.
Okay, good.
So I will not show that. Okay, next thing is now I have already showed you the monatomic simple fluid and water. Okay, so for water, I think if you, okay, so how should I? So for the water simulation, it's very, okay, I will start. Sorry, so I will talk about how to make these geometry files. If you have a simulation box of just the bulk water without these carbon walls, again you made these two carbon walls from whatever geometry builder you prefer. Once you have these two geometries, the next question is, right, I will add these two things together. The next question is how to combine them together in a simulation. So if I just load these two data files, you see it, the problem is that the relative position is not very ideal. If you just do this way, it will probably have some errors. The lamps will probably through some errors, like the items will overlap, especially in the bottom. So the way to adjust that is, again, using a script, right? Using a lamp script to take advantage of this read data command. Do this twice. So the read data command can be used multiple times in that case. And you can see here, I'm first reading in the initial .d, which is a bulk water, with just a simulation box for the bulk water without the carbon walls. And I will use the read data for the second time to read into the carbon walls. But here, you should pay attention that I will set the offset coefficient to be these values. That means I will have two placeholders for the water molecules because they are two atom types, right? And I will just add one atom types on top of that. And in terms of the position, in order to avoid this situation, I need to shift the carbon atoms. So if you imagine that when I read the data for the second time, I can just shift the carbon walls to move downward. 2 angstroms should be enough to avoid the atom overlapping problem. So that's why I shift 0, 0, -2. That's where this -2 comes from.
Sorry, Yuanhao.
Before I want to ask this question, I'm going to do a little bit of a teaching assessment here. And so, Yuanhao, pick somebody at random who's in the room right now, who's going to answer a couple questions.
Oh, so sure. What question?
No. I'm asking you to pick. You pick a student in the room, and I will ask 2 questions. I'll ask a couple questions of that student based on what you just taught. So that this is really feedback for you. So pick somebody. You don't have to pick Siddharth. He's a very welcome guest with us, but he doesn't spend his days thinking about lamps. So it may be a little bit more. I'm guessing you don't spend most of your day in lamps. Same here. Okay, Yuanhao, pick somebody in the room.
Okay, Mahu. So.
Okay, Mahu has been picked. All right. So Yuanhao, go back to the script. Okay, here's my first question. Mehul, what does that -2 at the end, what is that doing?
I have no idea. I was actually curious and I was going to ask the same question to you.
Okay, Yana, pick somebody else.
So what? I don't get the point. So what was your question?
Oh, okay. So Yana, I asked Mehul if he could explain what the -2 at the end of that line does. And
which one? This two?
This -2. And
but I just explained that -2, right?
Yes. So this in the middle, in this is a perfect parable of how teaching works and doesn't work sometimes. When you know something, and I know, I'll say this because not because I'm a Lance genius, but because I've spent my fair share number of years doing this stuff. I know what this line is doing. But I'll say, Yuanhao, that the way that you covered this line was extremely quick. For somebody who knows what this is, it's very obvious. For somebody who doesn't know, it was very, very, very quick. And so this particular kind of teaching actually, unfortunately, doesn't serve anybody well. It bores the people who know, and it doesn't make sense to the people who don't know. Finding that sweet spot in between he's very challenging. And that's what good teaching is all about.
I see. Okay.
Anybody here use append, or anybody here use add lines in general in read data? So does anybody use this kind of stuff? This is kind of stuff.
I mean, the 4 zeros are a bit more confusing than the shift. So
Yes.
like, talking about that will take.
Yes. So this is the question. This is actually how I expected it to go. I would have expected that for those of you who use, okay, so this is a 100% judgment-free zone. We're just trying to. This is really an assessment. If you don't understand, it's Yuanhao who should be taking the feedback on this. Who understands what the -2 is for? Raise your hand.
Okay, I will try to explain that again. Okay.
Say it just because I kind of knew beforehand.
Okay, but we're just getting the data here. This is really, you know, what teaching evaluation is all about. Just this is not about people being smart or stupid. It's like understanding how effectively something is communicated. So for whatever reason, you know what the -2 is about, and you know what the -2 is about?
Yes.
What's your guess?
It shifts a little balance or
It shifts the entire box. What would be the purpose of shifting the entire box?
not the entire box, but the glucose estimated.
Yes. So that's correct. Who knows what that first 2 is about?
All right. Something like that. It's because you have to reserve an additional type for labs to be added to. Which is very confusing because it should know beforehand that it's going to be added, and you cannot add anything after that if it doesn't know that there are different new items of coming in.
Yes. So Yuanhao, so Saptarshi has explained now what the -2 is about. I'm not sure if you could hear that. Why don't you start again and explain what that first 2 is doing?
Yeah.
A lot
Okay.
of people will come into this situation.
Sure. So first of all these things you should you will have the reference in the LAMPS documentation. For example, if you're not sure about the read data command, there's a very detailed explanation in the LAMPS documentation. So the offset 2, that means the 2 is the placeholders for the previous item types, because you have to set some positions for the previous data that you read into. Because I first read into the water molecules. And as we know that the water molecules has 2 atom types, hydrogen and oxygen. And when I use the read data for the second time, I'm reading the carbon atoms, which is the extra atom type, which is carbon. So in that case, I have to set the offset to make the 2 placeholders for the previous atom types that I read into. So there are 2 of them. And that shift has 3 positions. You can understand X, Y, and Z positions corresponding to that X, Y, and Z. So the reason that I'm putting a -2 on the Z position is on the Z direction is because of, if you think about, if I just put this number to 0 in the Z direction, that means you just read into the carbon walls at the original relative position. So that will result in some atom overlap in the bottom region. That is not good. But if you see this as a -2, that means when you are reading the carbon walls, when you're reading the solid atoms, it will have a relative position that is downward 2 angstroms. So that means the carbon atom will no longer be here, but instead it will be somewhere here. So the top carbon will also move down for 2 angstroms. The unit, by the way, the unit is the real unit, and the length unit is angstroms. So that's how that -2 works. So is that clear?
So that's the audience. Is everybody clear now about the -2?
So I'm not clear about the first 2 and the 4 zeros. Can you explain about them again?
The rest of 4 zeros, I'm not sure either, because I cannot memorize the LAMPS documentation. So that's why I mentioned if you want to know all the parameters, what do they mean? You have to go to refer to the LAMPS documentation.
So I have a question. The line before, when you feed the data and just that data, you put read data and then the name of it. Why do you have the extra atom types 1? I guess that
because okay, so that's a good question. So notice I have extra atom types 1. That's prepared to be. That means I have to read the data for the second time. When I read the data for the second time, that 1 determines how many extra type will I have on top of that initial .d. So you can think about their total number of 3 atoms in that simulation: carbon, oxygen, and hydrogen. There are total number of 3 atom types, right? So that is very clear. But when you are reading the using the read data command for the first time, you are only reading into the water molecules, in which case you only have two atom types. But you know that later you will add one extra type, which is the carbon. So that's where the number 1 comes from. And this 2 again comes from the previous placeholders for the 2 atom types. But I'm not sure about the rest of the 4 parameters. It all has its meanings, but you have to refer to the LAMPS documentation.
My question is going to be what the 5th zero is, because I really don't know what the 5th zero is. I can tell you what the 2nd, 3rd, and 4th zeros are. There's no offset in the number of bonds, in the number of bond types, in the number of angle types, and the number of dihedral types. That's
Yeah.
yeah. I have no clue what the 5th one is.
I'm not sure either, unless I go to the documentation.
I'm actually, well,
I think that there are only 5. Well, yeah, but it's $4 total. I don't think there's 15.
Okay, let's go to the read data command. Let's go to the.
It's good to learn different ways. You know, this kind of stuff, by the way, I said this for everybody's benefit, including Sarah, who's joining us. This kind of stuff, on the one hand, this is not rocket science, and this stuff can feel like, I mean, this is not intellectually noble, like learning how to do.
You see, there are 1, 2, 3, 4, 5. There are 5 parameters here after the offset.
So what is that 5th one? Let's append offset.
Offset to add improper types. Improper type.
Of course. Okay.
Yuanhao, have you tried using the combined data set and the translate feature of Ovidio to do this?
No.
That is exactly the thing that you're doing now is exactly what I tried to do for my project. But once you have then another oxygen coming in and stuff, it becomes super hard to do the plants. And to add up what Jerry said, it's not rocket science, but I spent literally like 2 weeks working on it to realize that it's becoming more and more complex. And each time I have to run the LAMP script to realize that there's an error. So if you go to your Ovidio, and I'm sure that Junji knows a way in media, but if you in modifications.
What?
In add modifications.
Add modification.
Right. If you come down to combine data set.
Where is that?
One down from what's highlighted. Just go one down from the one that's highlighted. And then you can select the second one, and then it combines them together, and then it gives you a data file, LAMPS data file.
Okay, that's interesting. I will look at that later. Okay.
Right.
Yeah.
You can also use it translate, and then literally just translate it here, and usually you can see if the gap seems reasonable. So I think the one that you're doing is more efficient if you want to do number of batches, but this one is more.
Yeah, that's good to know. Okay, I will. So yeah, again, everything is very clear on the LAMPS documentation. I really like for each command, if you are not sure about how to, yeah. So
very clear once you know it. I won't agree with that.
Okay, I will quickly jump to the ionic liquid given the time consideration. So So for the ionic liquid, I want to especially talk about the force field setup, which is very complicated in if the molecules are like very complicated. So I will first load into a single geometry file. So the idea of this simulations is if you have a single geometry file, okay, I'm opening it both in Ovito and in VMD. So I can teach you how to do the VMD very quick here. So you go to graphics representations and you go to drawing method. You don't want to the lines. So it's not very ideal. So you go to CPK, right? So you go to CPK and it will give you a better looking image of this molecule. This is ionic liquid, by the way. So this is made up. So if we look at the structure of that ionic liquid is actually BMIM plus and PF6 minus. So that's the one from Chen Shao's paper. And you can make the resolution to be bigger, to bond resolution and sphere resolution, to make the picture to be even more better looking. So let's first look at how many atoms are there in a single molecule. There are 25 different atoms, 25 atoms. So this one, so you can see this is carbon, is made of carbon, nitrogen, hydrogen, and how to read these two elements, P and F. So I can't hear you.
F is fluorine and P is phosphorus.
Phosphorus and fluorine, yeah. Okay, good. So there are total number of 25 atoms in one single molecule. So this is a pretty complicated molecule, and one part is carrying the positive charge and the other part is carrying the negative charge. So the question is how can we set up this simulation in labs? So let's look at the so the reason why I'm showing the both representation is in VMD you can see the bond very clearly, and in Ovito you can see the atom types. So I will show you a table. So here, that's too small. See, no. Better. Okay. So there is a table to compare these items in a LAMP setup. So as I said, there are total number of 25 atoms, but it's not necessary to make 25 different atom types in a LAMP simulation if you want to do this ionic liquid. Why? Because there are some, we can see that there are some carbon atoms that has the exactly same environment. For example, these carbon atoms and that carbon atoms, right? Sorry, this one. So these carbon atoms and I'm trying to. So yeah, at least these two carbons, they are sitting in the same environment. These two carbons. Maybe this is a better way to look at. Okay. What I'm saying is these two carbons, you can group them as the same type because their environment is exactly the same. Are they exactly the same? And these carbon atoms are different, including this one and this one. So there are total number of 5 different carbon atoms in that geometry. So that's why I have 5 different carbons, right? 5 different carbons. I call it atom type 1 to 5. But they have exactly the same atomic mass, which means they are, six types of different carbons, but given the same atomic mass, that means they are all carbon atoms, but the environment they are sitting at are quite different. That's why I have six atom types for the carbon. And fluorine, I have 1 atom types. For the hydrogens, we can also distinguish the hydrogens, like all these hydrogens here are the same. And these two hydrogens that are sitting on next to these carbon atoms, we can treat them as the same. So as a result, there are total number of 3 atom types for the hydrogen. And again, these atomic masses are the same. So that's for the carbons, fluorines, and hydrogens. And we have some nitrogen, like 2 nitrogens are sharing the same atomic environment. And how to read this?
Phosphorus.
Phosphorus is a atom type that I call it 12, atom type 12. And for the graphene walls, I will set one on the top, 1 on the bottom. So they are 13 and 14. So that's how I distinguish the different atoms based on their environment. If you look at this LAMP script for this ionic liquid, you can see that when I read the data, I include a potential file, which so these are all from Cheng's work. So which Cheng put the extra potential file that to be a single file to define all these force field. So there are 12 atom types in total, which I just described how to distinguish the carbon atoms, the hydrogen atoms, and also the rest are very easy because they are just single ones of them in this molecule. And we have to pick up a pair style. We know that they are carrying the charges, so the LJ cut Coulomb long is a good option for this pair potential. And so this part is the most important part. So maybe from some literatures or from the UFF tables, whatever resources you will get the pair coefficient within these interactions. So within these atom types. So these are like for pair coefficient that are interacting just for these carbons, hydrogens, nitrogens, like all the interactions within each atom type, like 1, 1, 2, 2, 3, 3. After you define all of this, you have the pair modify command, which you have a mixing rule. The mixing rule is based on geometric. There are many other options, but the geometric one is the common mixing rule that we see, which means the epsilon is the square root of 2 epsilon, the product of 2 epsilon, and the sigma is the sigma 1 plus sigma 2 over 2. So that's the geometric mixing rule. And once you have that, you will have an idea to figure out what's the pair coefficient between 1 and 2, let's say 1 and 3, 2 and 3. So they are all based on this mixing rule. And after you define that, you will also define the intramolecular interactions. So that is basically how you set up the bond. So the bond coefficient, you can also look up from some literatures that you got this coefficient. But this unit are in kilojoules. You have to convert to you have to convert to this unit. And because if you want to use real unit, this is how lamps work. how lamp theory unit work for the energy scale. So these are all the.
It's worth noting here. These are kilojoules per mole versus kilocalories per mole.
Oh yeah, exactly, yeah.
That's important. There's a very large difference.
Yeah. So let's look at how these things are like. First, you have to like exactly like the pair style, how to define the bond style. Harmonic. So what does harmonic mean? So let's go to the LAMPS documentation. Bond style harmonic, that is the like the spring interactions. This K is like a spring constant, and R0 is the equilibrium bond distance. But but note here that there are two parameters after the harmonic bond style. One is the energy per distance squared, which is a constant K, and the other is R0. So that's how the bonds coefficient are considered here. So all these bonds defines the intramolecular interactions with these are the bonds are defined here. One is the energy and the other is the length. So this is how the bonds are defined in this system. I think it's very clear if you make an extra potential field when you are deal with these complicated molecules or geometries, because you can put all these interactions into one single file, and when you're building the other, like running the other LAMP script on top of that, you can just include that file in your simulation. So after the bonds, you have to define the angle type. So similarly, you define the angle scale, angle style to be harmonic. And you can also refer to the LAMPS documentation about what does the two coefficient mean after the harmonic angle style. And after you define all these angles, and after that you have the dihedral style. So that's because of the particularly interatomic potential they pick up in that simulation. Okay, I will finish within 1 minute. So after you build these geometries, let me show you how these trajectory files look like. So the colors are not very good. Okay. This is how the simulation, how the trajectory look like for this ionic liquid. Okay, so that's all I want to share today.
All right, let's have a round of applause.
Thank you.
You have to see my answer there too. Overarching questions for Yuanhao? All right, I'll throw one question there. So, Yuanhao, you showed a harmonic potential for the bond style and also for the angle style. By the way, as you hinted to, for the angular style, or for the angle style harmonic thing, you have an angular spring constant, and then it's your deviation from some equilibrium angle. That's your displacement. You square that, you multiply by the angular spring constant, you get energy. So here's my question: why is harmonic such a popular style? Why does it come up so often? What's the fundamental physical reason? Because you'll find people using harmonic stuff all the time.
Yeah.
Why is it worthwhile? Or why is it a reasonable choice?
I'm not sure where to start to think about this question.
Okay. Anybody else?
It's repetitive. That's the one thing. Like a harmonic is kind of repetitive motion. Not like I'm thinking of an analogy on the atomic scale. Like the electrons move around. Like motion of electrons can be repetitive, and to up the scale we have kind of we need some repetitive. No, but that's not true.
I like some parts of that answer. Let's throw down, what do you mean by repetitive? What is repetitive about? So the function that Yuanhao showed, it's a parabola. So what's repetitive about a parabola?
So I was simply considering the simple harmonic motion, which we have some time period and stuff.
Sure. Okay.
So by repetitive, I mean it has certain time period and oscillation. So in that sense, I was thinking of how.
So that is true for the harmonic oscillator, but there are other oscillators that are also repetitive. There are all kinds of oscillators. So why harmonic oscillator?
Yeah, that's what I was thinking of. Like one thing is repetitive.
So I like the physical feature about that, although it doesn't explain why a harmonic oscillator out of the whole zoo. There's people in dynamic systems. They study literally thousands of different types of oscillators. The harmonic oscillator is the one that they teach undergraduates. So why that one out of all the oscillators out there?
So like I'm not aware of other oscillations, but do they have the concept of potential kinetic energy?
Yeah.
These two energies are the.
Yep. They all have the concept of that, and it's just some other function other than that one. The harmonic oscillator is the one that has the quadratic potential energy function.
Is that because it's the displacement is not large, bottom of the well, it's defined, it's changing probability. Excellent.
So if you're at equilibrium, this is the lesson from all around, and we talk about this in molecular simulation amongst other places. If you're not far away from an equilibrium configuration, the bottom of any potential well, if you try to approximate it, you could try to do the most reasonable thing in the world, which is to write a Taylor series for the energy. The constant term doesn't matter because constant energies never matter at all. What you set as your zero doesn't change anything. The constant term in the Taylor series doesn't matter. The linear term, when you're in equilibrium, is zero, which is sitting right at the bottom of a well. So if you do the first derivative, that's also just zero. The very first term that shows up when describing any point of mechanical equilibrium is the second derivative, and that's exactly the quadratic term that Yuanhao has there. So that's why this shows up all the time. In general, it's not an accident that you see harmonic approximations all the time. It is the first thing that matters. It's the first variation that matters that shows up anytime you're in equilibrium.
Oh, I see. It's from the Taylor expansion, right? Something like Taylor.
I think personally, because I come from the background that I come from, I think that that's the best way to rationalize where this particular functional form comes from. It's the very first term in the Taylor series that is not zero that matters. The constant term is not zero. You can set the constant term for whatever. You can set it to 57.5 or 3 billion. It doesn't matter because it's only changes in energy that matters. So whatever that constant offset is, it doesn't change anything. It's the first thing that changes that matters, and that's the quadratic term. So that's why you'll see harmonic used all the time. There are other kinds of oscillators out there, including Subtarshi actually uses non-harmonic oscillators in his code. You know, the butane molecule, I mean, this part, I don't know if this is something you dug into, but there's the cosine squared. Yeah, exactly. So there are that's a non-harmonic interaction. Of course, you can just run your PTA code. You don't care what the world the potential actually is. You don't care, but you actually run code with a non-harmonic potential. Cool. Round of applause for Yuanhao, and we'll move on to Subtarshi. All right. So Yuanhao, we're going to turn Mahul's laptop around at the board, and we will see how this works. You let us know if this is.
Actually, if you like wait for 10 minutes, I will go to join you. Or okay.
Oh, you can get here in 10 minutes?
Yeah.
Okay, all right. We'll see you soon. Don't drive too quickly. I don't want to hear that you're in a car wreck on Forbes because you're rushing.
No, 10 minutes maybe not.
All right, we'll see you in a moment.
Okay.